then he was showing me exactly endoscopy. You would go inside the stomach, you would get samples, you would even, put stitches in the stomach. But the point is, in the stomach you won't be able to see. Fiber optic is using the same concept, but how? It's exactly like a wire, but what happened? The core has more index of refraction. The light goes in, it's trapped, won't come out. But the cladding has less. So it doesn't matter how you bend that, the light is going to go through. See, the reason why we can see through, if there's a tunnel, we can see through all the way. What if that tunnel has a curve? You won't be able to see it because light won't go through. So I have seen that how important the fiber optics is, and Dr. Gray knows. Some people even can get PhD in fiber optics. Really, they can.
Yeah. Did you all talk in lab about total internal reflection? Are those words that are familiar? Okay, so fiber optics use that principle.
Fiber optics, yeah. Well, it's endoscopy. Well, of course, like I said, unfortunately, due to lack of time, because this concept is so important, how you see things are different. Your perception is always not exactly the way you see things. Now, I see sun in the sky. That's not the actual position. Can anyone tell me why? The sun sets, right? Is that the actual position of the sun? Why? Why do you have it between? Exactly, atmosphere. See, it's not dense like water, but you can see the old days, people would think, well, we'll find water in a railroad track, and go, they never find that water because light refracts. When you see the moon, that's exactly not the way it is. That's not the actual place, because the only way you can see is the Hubble telescope. But of course, it's not for us, it's for scientists, because Hubble telescope is illuminating that atmosphere. They take the best pictures of universe, all the galaxies, and everything else. Hey, Dr. Gill, what was the third one I was wondering?
The second law of thermodynamics with spring.
Okay. Yeah. Folks, I did explain that it's a word of spring is. Sorry, folks, we're a little bit unorganized here because it took us for a long time to get this word of spring.
Let's see. Are these your Hooke's law springs with big springs and these springs?
Oh, right there. Okay.
These springs. Okay.
Folks, this is a simple thing. Albert Hooke was a great scientist, and I don't know how true it is. They said Isaac Newton got some ideas from the Hooke. And the Hooke is so famous for the spring. And it's amazing, this spring is used in technology a lot. You push on it, it's pushing back. So what I did, I compared with the Earth. The reason why you have now feeling your weight, because Earth is pushing on you. You may not feel it, but amazingly, it's proportional to your weight. If I weigh 200 pounds, Earth is pushing me 200 pounds. If I weigh 150, and it's amazing, the deflection is proportional to the force. I get more force, more deflection. But it has to go back to the state of equilibrium. It doesn't matter how much you push. See, as long as you don't damage the spring, it has to go back. But there's important thing, and I don't know why the scientists never explain this. See, when I push this back and forth, what will happen? Thermodynamic comes in equation. So what happened? This is getting hot. But unfortunately, what happened, I lost that thing. I had a glass thing made on this. And then I had thermometer, which is non-contact. So in other words, you can feel it without the thing. When it goes back and forth like this, you never feel the heat. But that heat is the entropy. So in other words, it's a disorder. So that shows exactly is the entropy. But unfortunately, I don't have it. But I want to show you, anytime you have any motion, no matter what, the second law automatically comes in equation. That's why the universe, like I explained before, everything works with the second law. You have electricity. You hook it up to your whatever, you do some work. But always in between, you have 100% input, but you get 97 output. That is so important. That's called efficiency. So in between that 3% is what? Is the entropy. Always you lose something. There is no way that, Dr. Gray knows, he's a physicist. There is no way that you can input 100% and you get 100% back. Always there is entropy. So of course, if you have any question, you can ask later. Let's see which one. Michael Faraday, that was my favorite one. Folks, let me show you here. Michael Faraday was a great scientist, and you may not believe he had no education, formal education whatsoever. Folks, I think you're going to have to come closer a little bit, because the reason why these are a little bit, let me get everything. He discovered one of the most fundamental things on Earth, which after like 180 years, nothing has been changed. We have improved that electric motor, maybe 100%, but the principle is not changing. It's exactly the same thing. When I was 10 years old, my brother was a good technician. I made one, and this is exact replica when I was 10 years old. But I just gave one to Dr. Gray because he's my favorite scientist. But the concept is not changing. What Mr. Faraday did, of course, I have the picture over here somewhere. Let me see where that is. Let's see where that one is, Dr. Gray. There was another.
Which one?
This is the induction. No, there was another one with the picture. I think it's here, Dr. Gray.
Not this one?
Yeah. Oh, right, yes, I'm sorry. Yeah, right there. Here's the picture right there. Let me show you one. Dr. Gray, I was wondering if we can get, let me see, where are my 12 volts in here? Of course, I can use the other one because this is so powerful for that. Before I try this, I want to show you something. See, when Michael Faraday did this, he had no idea about the Henry Lorentz forces. And Henry Lorentz was an amazing scientist. He was one of the greatest ever born. Of course, Dr. Gray knows he has so many ideas about the relativity and so on and so on. The entire concept is moving charges in a magnetic field. That's simple. See, your speaker is using the same thing. Your pendulum, this is the electronic pendulum, is using the same thing. I mean, your everything, almost anything you use in your car, like your starter, anytime you have particles moving in a magnetic field, it will react with the magnetic field. That is the whole idea. Well, of course, it's simple. That's called Henry Lorentz force. Well, of course, I have the photocopies. You can have it. But this is the same concept. See, what I did is the simplest electric motor ever. To be honest with you, Dr. Gray, I've never seen such a motor in my lab. Have you ever seen?
I've never seen one like this.
Because
used
this
as a
one,
production
when I was
motor.
kid. And this is the simplest form. If you don't have that commutator, so what happened, this is changing the direction of current. So in other words, it's the flow of electron. If I don't have that, what happened, this will be energized, and then on a magnetic field will stop. But why this is attracted, this is attraction, repulsion. The reason why is changing the flow of electron. Can you see, folks, that? See that cut over there?
Right.
See?
Look at how the copper is cut and how it's going to reverse the direction.
So this is going like 180 degrees, and then at the same time, what happened? This is energized, it goes attracted. But here, it's changing. So in other words, we have repulsion, attraction, repulsion, attraction, repulsion. Let me show you. how it works. And see, if you know exactly how everything works, you have to start from the scratch. You don't have to know everything. But if you start from scratch, if next time someone asks you, yeah, how the Henry Lorentz works, I say, it's just easy. This patch is dead, I think. Oh yeah, it's not good now. Well, of course, it's not a good battery on that. Did you see, folks, what happened? So I was wondering, how could you reverse them from clockwise to counterclockwise?
Switch the polarity.
Fantastic. So in other words, what you're doing is exactly Henry Lorentz work. You're switching. So what you're doing, the flow of electrons are different.
Watch the sparks at the contacts on the commutator.
That's not a good.
Every time the current is reversed, there's a spark.
Exactly, yeah. Well, folks, and this one is much more stronger because what I did, I converted AC. This was 115 volts. You see the armature? But look, instead of 1, see, mine is acting 180 degrees, and guess what? This is acting 30 degrees. So every 30 degrees is energized, de-energized, energized, de-energized. And guess what? This was 7,000 RPM. But what I did, I converted from AC to DC. It's just simple. It's exactly the same concept. But now here, instead of having wires like that, I have permanent magnet. It doesn't make any difference. The interaction is the same. And I think, Dr. Gray, on this one, I'm going to have to use the 12 volts.
It's a big battery?
Yeah, that will must be much better. See, folks, this is exactly like this one, but mine goes 180 degrees. See what happened? North, south. So while this is north, this is also south. It goes attraction, repulsion, attraction, repulsion. Well, of course, it's not a practical idea because in a factory, let me show you. Factory, they use like this. Gee, it's how hard it is. Did you see that? It's round.
Those are the magnets inside.
Yes. Well, of course, this is, not good anyway. Just wanted to show you. But see, it works. Concept is the same. It works. Of course, this is a little bit powerful, and they work also 6 volts as well. Let's see. This is so powerful for this, but we have no choice anyway. The RPM is much better because the magnets are so strong. Okay. Can you feel this? See, that is hot. You see what happened? Okay. Now I'm going to show you this one. You can see how this one goes.
In lab this semester, you all are going to build a simple motor. That's one of your lab activities.
Yeah, folks, I can help you anytime you want. So, look, folks, and it doesn't matter where you put the wires because no matter what, one is going to be energized. It doesn't matter. Okay. And this goes 7,000 RPM. The closer it is, the better. Look. Now we change the polarity. Look. it's just easy. But what I wanted to show you, Michael Faraday did fantastic experiment. It's called induction. Without the induction, there is no way we can survive. Let me give you a little bit history. Thomas Edison had no education. Well, of course, he was a good, inventor. But always, he was insisting on a DC. DC is fantastic in a smaller scale. There is no way we can have power in DC. Well, I don't know if you guys have seen it. Well, it was like 100 years ago, and I saw a science movie, something like that. There was so much wire in New York City, you could not even see the sun. But unfortunately, at that time, people had no education. They didn't know that, Thomas Edison was lying. And here comes Mr. Tesla. Tesla is one of the, Dr. Gray knows, one of the greatest scientists ever born in history. So Tesla saved the world because AC is easy. But he had the knowledge of Michael Faraday. Michael Faraday had one magnet. He moved a coil like this inside, in and out. That was the greatest experiment in the history of science. And then everything was connected to a meter. And then he saw it's moving in, the meter is going backward, moving out. And then he had no idea that he invented the AC. I'm going to show you guys in a minute. That was AC. He didn't know. It took another 60 years. Mr. Tesla came and he built 120 degrees. He built 3-phase AC motors. He was a great scientist. And after that, some American scientist, his name was John Barty, he had 2 Nobel Prizes for the transistor. You can convert DC to AC by transistor. But Michael Faraday was so smart, he did everything mechanically. He switched on and off, on and off, on and off. And then he had 12 volts, but he got AC. If you have no AC, there's no induction.
So AC means that...
Alternating. Yeah, I'm sorry, I have to clarify.
Yeah, the polarity of the voltage switches.
It goes like a
sine wave.
See, if we have no AC, there is no way we can have a life. Because AC, you can have transmission lines, you can have AC from Chicago to here. With DC, no way. You need millions of stations from Chicago to here if you have DC. But with AC, no. AC is amazing. What they do, they boost the AC like 200,000 volts. Or what they do, they bring the current down. And then by the time it gets to your houses, you must have seen those huge green boxes. Those are transformers. So the transformer was also invented by Michael Faraday. I'll show you in a minute. Transformer means you have one coil and then you get induction with the second coil. But the point is that second coil, you can have 6 volts, you can have 12 volts, you can have 10 volts, but with DC, it's impossible. So Michael Faraday did that, and then I'm going to show you exactly how he did it. And he had this unique way of doing this. He had a ring like this, and this ring, I don't know exactly what the measurements are, but this is exactly what he did 180 years ago. So we have one coil here, and there's a little gap in between. So what he did, he had DC, and then you can see the picture over here, but that's not Michael Faraday, it's just a remake. But that's exactly the way he did it. So he switched on and off, on and off. So what happened? He got from the DC, he got AC because of changing magnetic field. And due to that AC, this coil, we got induction on the second coil. Let me tell you what the induction exactly is. Anytime we have change in intensity or change in polarity, we have AC. And that AC makes the induction. With the DC, if I have that 12 volts here, I have a coil over here, right? If I put another coil even if I put iron core inside, there won't be any induction. But see, if I connect it to the 150 volts AC, we will have induction because of the changing magnetic field. So what he did, he had this switch on and off, on and off, on and off, and then what he did, from the DC he got AC. This is the one I invented. You see that thing over there? So this is changing magnetic field on and off, on and off, on and off. Well, of course, it will take forever, but I'll give you the photocopy. See? On and off, on and off, on and off. So if I have AC over here, the output will be AC.
Because there's a commutator on.
Exactly. Because
Just like on the motor, there's
Exactly.
other contacts here. Okay.
folks, the important thing about the physics is the reversibility of the laws of physics. Laws of physics is amazing. I compare the laws of physics like a two hands balance scale. If you have gravitational potential energy, the loss of gravitational potential energy is equal to gain in kinetic energy and the loss of kinetic energy. So in other words, it doesn't matter how you move, always laws of physics works the same way. You lose something, you gain something else. And in technology, they call it trade-off. There is no way that you gain something. Always, the first law of thermodynamics tells you always you need to put in energy, otherwise you won't get anything. See, if I rub my finger, if I rub my hands like that, what kind of law is that? I was wondering. Can you tell me? First law of thermodynamics. So converting mechanical energy to thermal energy. We've done this when we were in high school. We're rubbing like this. So what you're doing, you are converting mechanical energy to thermal energy. But in your car, it's reversed. You have the thermal energy converted to mechanical energy. And then the rest goes out from your exhaust or your muffler. That is the entropy. You never get 100%. So that's so important you guys know that laws of physics are reversible. No matter how you do it, there's always a trade-off. Like a lever, seesaw. We have one kid over here, one kid on the other side. That kid is twice as heavy. All you do, you trade off for the distance. If the light person moves farther from the fulcrum, they will equal. Even though she or he is double its size, but see, it's always a trade-off. You lose something, you gain something else. Laws of physics works perfectly. It's amazing how they work. And this is a transformer, folks. That's exactly what Michael Faraday did, but it wasn't like this. But I just wanted to show you guys how important it is. They call it a step up and a step down. All the electricity we get in this city is not generated in here, generated in Hoover Dam, right? But the transmission line comes here, they step up with the transformer. Well, of course, it's not like it, but the concept is the same. They have high voltage here, and they have low voltage over there. And then when it comes here, everything is reversed. So if I reverse this, it's going to be step up. If I reverse the other way, it's going to be step down. But transformer is always following the same rule. It's induction. If you don't have the iron core, the induction will be much less. So Faraday knew that iron, and amazingly at that time, the atomic structure didn't even know what the atomic structure. But the line of forces, he knew. How could someone without any education know this much knowledge? Because he was doing the experiment. And in history, anytime you go on an experimentalist work, Michael Faraday comes in. Chemistry, he was genius. With physics, he was genius because he was doing experiment. So it's so important you guys know that if you're doing experiment, Dr. Gray knows, experiment must be thermodynamically isolated. What we did over here, it was not thermodynamic because of the air pressure and the air is stopping my pendulum. If I take this to the moon, that's aerodynamically what? Isolated. No matter what, always you have to do that. And then you have to be conclusive. Everyone knows Mr. Allen, he dropped 2 balls. That was not new. Someone did 2,000 years ago, his name was John Philippus, but unfortunately he had no idea why the small ball with the big balls, they accelerate at the same rate. He didn't know. And then there was another scientist, his name was Stephen, but the Stephen was a good physicist. He dropped 10 kilogram and 1 kilogram lead balls in the church. But he had no idea why they accelerate at the same rate. And then here comes Mr. Italia, he solved the problem.